All right, well, thank you so much. This realization of this code kind of just happened during our project, and I thought you guys might be interested to really see how we did it in a not very complicated way. So I hope you guys get something good out of this. So a little background, a little introduction. What is Vortex Southeast? Well, it is a verification of origins of rotation in tornadoes experiment, southeast. There were other vortex projects before this, Vortex-1 and Vortex-2. They happened in the Great Plains and Tornado Alley, if you want. So why did we have this one in the southeast? Well, the main motive was that the southeast suffers from a disproportionately large number of tornado deaths when compared to other tornadic regions in the country. So while we may get more tornadoes in the so-called Tornado Alley, we still get a lot of tornadoes in so-called Dixie Alley in the southeast, and there's a lot more deaths, and which is not something you want to hear. So this project consisted of both social and physical science objectives. However, mainly I will be discussing about the physical science in this. But being in the southeast, this required a new approach to tornado research. So I'm not sure if you can see my cursor or not, but here I have a picture of the tornado tracks, the rotation tracks that went through the southeast on a big 2011 outbreak, a very famous tornado outbreak that kind of motivated mainly this study to happen. And on the left, you see a picture of a tornado that happened during that one. Sorry, that's the only picture of a tornado I have. I apologize for that. It's just kind of gives a motivation. And so our region that we studied in is in northern Alabama and southern Tennessee, kind of where you see a lot of tornado tracks from this particular outbreak. So just a little background there. And so why did we need to reinvent how to do tornado research because of this project? Well, so most of our tornado projects happen in the Great Plains. If you've ever been there, it's flat and it's no trees, and it's just, you can see for miles. And so on the left bottom here, I have a picture of what it looks like, that's actually in North Dakota, and so northern Great Plains. But you can see the base of that storm, you can see for miles. But on the right is kind of a failed deployment spot for, in the southeast, in northern Alabama. There's trees, there's hills, the cloud base is really low, the road network is curvy and sparse, and you can't really do a radar-oriented or any other situations, because how do we get to the tornadoes? Through the road network. And so it's not very good chase country down there. So we wanted to reimagine it and kind of still be able to study it. And so the Texas Tech University Atmospheric Science Group decided to address this issue using our mobile stick nets. And so there's a picture on it on the front, on the title slide, and I have another picture of it here. So we put together 16 stick nets all over northern Alabama and southern Tennessee, as you can see in our little inset picture there. And we called it the StesoNet because there's mesonets and these were stick nets, and so we were like, oh, let's be clever. But so again, to address our lack of mobility, we had those set up semi-permanently in all 16 stations in that grid that you see in the middle there. And each station recorded data at 10 hertz, and then on board that station, the data is averaged over 1 minute and created 1-minute files so that were sent to our data server through the cell network. And so because of all of our stations had to be semi-permanent, and because of how broad the stations were, we had to monitor how the power was being supplied. So as you can see, we see a big old solar panel there, and as you can see in the background, it's very cloudy and not much sun. In the southeast, there's not a whole lot of sun, so we had to make sure that all of our instruments were getting appropriate voltage. And so that's how we did that, and so using real-time data and visualization was important to that too. So that's a little background about our data supply. So now let's talk about how we visualized all that data in the real time to help us with research in our project. So a little overview. Here I have a little flow chart. We have the StickNet, or StesoNet probe, if you want, collecting data at 10 hertz, which was then averaged into 1-minute files, and then sent to our computer for analysis, where it ran 2 major scripts where we were able to visualize most of our data. So first, let's talk about the data files and how they're stored. On board each probe, LabVIEW, if you ever worked with LabVIEW, averages the 10 hertz data acquisition data into 1-minute files. And what are these 1-minute files? Literally just a string, one line of text, providing all of our information from that 1 minute. It has probe ID, the location of it, the date and time of when that 1 minute of data was, the temperature, relative humidity, pressure, wind speed, max and direction, and the battery. The file is then saved in a descriptive format with the probe ID, date, and time, because that helped us grab the real-time data when we needed it. And then, so every minute, one file would come in from each of the 16 stations and to our server, and then to our analysis computer. So that's just over 23,000 data files saved every day, and that's just data. That's not including the plots that we made from it and everything like that. To some of you big data people out here, that's not really a big deal, but to us, it kind of is. So it's kind of what we worked with. And this was a 10-week project, too, so it was 23,000 data files every day for 10 weeks. And so that's kind of just what the data looks like. And so that'll help you when we're trying to figure out, how do we find the data and parse the data. So moving on our analysis computer, we used cron jobs to execute our Python scripts. So we set a time every 10 minutes. The radar observation one was run, and every 5 minutes, our Meteogram plot was run. And so first, I'm going to go over to talk about the NEXRAD and the observations. First, when that script was started, the first thing we did was we pulled radar data from the NEXRAD stations. So your Doppler weather radars that are all over the nation, supported by NWS. And so how did we do that? Well, first, I'd like to throw a shout out to Scott Collins, Jonathan Helmus, Ryan May, Mark Korver, Jed Sunwell, and Gokhan for the short course, Interacting with Radar Data in the Cloud, that happened at the annual American Meteorological Society meeting this year. Really helped us out. We really appreciate it because it was able to introduce how to pull the NEXRAD real-time radar data off of Amazon Web Services S3 bucket. So I learned a lot from that, and so by using that, we were able to do what we wanted to do. So using Bodo, we were connecting to the AWS S3 bucket just by this simple, so also throughout most of my presentation, I'm gonna have these screenshots of code. I'm not gonna go through them or anything like that, line by line, I'm just gonna tell you what they are. But if you ever wanna go back to the presentation and kind of see some of the code that we have, that's why I provided it on there. And so the bucket is called NOAA NEXRAD Level 2 Radar Data. We know how it's stored on there. All the real-time data is stored on there in a specific format using the year, month, day. NEXRAD station, so it's 4-letter station number, like KHTX is the Huntsville one that we used, and then the file name. And we used that, knowing that format, we used it to grab our radar files off of AWS for the time we wanted, the real time we wanted. And so down here is just kind of how we, after learning the indices of where it was, using the date and time, we were able to create and export a radar list populated with PyArt data. So that's another big thing. PyArt was a huge help in this project, and we were able to use PyArt to get the data off of AWS and make it easier for us to plot the real-time data. And so, so thank you to that short course, but we get all of our NEXRAD data from AWS, so that's a big help. The data, is within 5 minutes. We are able to keep it, do everything within 5 minutes, so that's pretty good for the real time. So after we pull our NEXRAD data from AWS, we need to go into our 23,000 files per day and look for the StesoNet files that we need for either the latest data, 24 hours worth of data, which is for the Meteograms, but I'll get to that later. So to get the real-time StesoNet data, we just created this simple search directory function in which we have a start time, we have an end time, we have where the file directory is, and just simply whether or not we want a full data set or just the latest. So using glob, we pull all the files down for our specific time period. We then parse each string and append the data to an array. Again, if you remember that text string I showed you earlier, everything was comma separated, so we just were able to parse it out, knowing where each of the locations were in a predefined dictionary that we set up earlier. We were able to just append it to our NumPy arrays and do that. We then only grabbed the latest data, and we made sure, up here, if you notice, we made sure that all of our data was within 5 minutes. If for some reason a station went down, and the data that it was providing was more than 5 minutes old, that would mess with our analysis, that would mess with our real-time data. So we couldn't pull that. We just needed the latest data. And then we converted the data into pandas data frames for analysis, for plotting, and each pandas data frame contained all the probes, all the times we needed, but in this case, it was just the latest time. And so like I said, we're doing this every 10 minutes. And then once we have those StesoNet files, we do two different things with them. We are able to create an objective analysis of the grid, and we also plot the StesoNet station obs over current radar, which is an example of a loop of this is what we provided on, we showed all this real-time data on a website. I forgot to mention that. I don't have a screenshot of that on here. But using PyArt, Matplotlib, and basemap, we were able to plot the real-time radar data over our real-time StesoNet observations. So we were pretty happy about that. That helped us with our analysis because we were able to see the sort of the mesoscale weather patterns and see what kind of things are happening in the southeast. It's a different area than we're used to working in. And so on the left, we have a reflectivity plot. On the right, we have a velocity plot, if you're familiar with Doppler radar data. And so just simulations like this really helped us out. So PyArt and basemap really made this process of putting radar on a plot really easy. Using basemap is the hard-coded region, knowing where the StesoNets were, the stick nets. And so we encompassed that region, and just simply using basemap from the code you see here, we define, okay, we want the coastlines, we want the counties, just so we can see our location. That really helped us out. And then in PyArt, it makes it easy to plot reflectivity products and velocity products running through. And also in PyArt, we also appreciate that you can just set a basemap in there, and we are able to plot the radar over a basemap. And it just, the PPIs that you're seeing, planned position indicating images, are just two-dimensional looks at the broad region of all the storms in that area. So after we had the radar data on there, we plotted the StesoNet plots over top. And that's just simply knowing the locations, because the StesoNet plots didn't change. We just used the Latin log to plot each point on the map, on the base map. And we were able to do that, and then just using like display.plot point. Then we used text annotations to display from our pandas data frame. We were able to display the latest data on each of our StesoNet stations. So we did this in a loop, in a for loop. As you can see here, this for loop here for the location of each one and for each probe. We went through and used text annotations and found our way to plot the temperature on the top left, the dew point on the bottom left, and the station pressure on the top right, as well as the station name. And so doing that, the next thing, sorry about that. So that's how we got our radar data over the plots. And so we ran this every 10 minutes. The data was real up to 5 minutes, real time. So that helped us out with that. And then so after, we also made, at the same time, running concurrently, we were able to plot gridded objective analysis of the grid, the StesoNet grid that we had. And so here's an example, and here's a moving example. This is over the radar. We just contoured it. We didn't fill it. Then on the right here is our fill with the wind barbs, because if you put these two together, it's cluttering. What we use these for were for our derived variables, such as equivalent potential temperature and virtual potential temperature. I'm not sure how familiar we are with our derived variables, but just a little overview. Why we wanted to show these objective analysis plots is because virtual potential temperature helps us figure out the instantaneous density of a parcel. And with changes in density, you can create vorticity, baroclinic vorticity, which tornadoes spin, you need vorticity for them. So that helped us try to figure out where regions of high vorticity along the surface were. We also and so Python, of course, was just used to code this equation up, as well with the same with equivalent potential temperature, which quantifies the potential buoyancy of a parcel. If a parcel has high equivalent potential temperature and it gets taken into an updraft, it will accelerate a lot faster than one with less equivalent potential temperature. And so an acceleration is good because that stretches our vorticity and creates tornadoes. So that's kind of why we wanted to investigate the mesoscale region and in between, because storms pop up between the probes. We need to know kind of at least what an objective analysis is doing. So how do we do that? We interpolated the StesoNet observations. First, we created just a grid of regularly spaced latitude and longitude points, simply linspace and mesh grid, meshed them together. And then so we calculated our theta E and theta V, and then using SciPy's interpolation package, grid data, we used a linear interpolation because speed is what we were concerned with, and linear interpolation is the faster one. SciPy interpolation package was used to interpolate 5-minute StesoNet observations to get the grid. And so that's how we were able to find this here. And just kind of a thing I'd like to say, this is a really high gradient of equivalent potential temperature. We didn't see that a whole lot there. There was like a boundary that was happening. And so that's kind of why we had an interesting case here. All the storms were popping up over here, and we were concerned with which ones were popping up in areas with highest equivalent potential temperature. All right, and so that's how we did our objective analysis. And again, all in real time, provided on our website within 5 minutes, run every 10 minutes. So those were our observations. Those are our two-dimensional observations over space. Next, we wanted to figure out our observations over time at each station. And so we did that using meteograms. And so we wanted to figure out what the weather pattern, the mesoscale weather pattern was like at each station over the past 24 hours. We wanted to see the changes. And so we did that. So first we had to pull the StesoNet files from our server for the past 24 hours. This is the same slide I already showed you. It is showing the latest data. Pulling 24 hours of data is actually easier. We just do our start time and end time within 24 hours. We Glob, again, pulls all the files that we wanted in this time period because, like I said, each text file was descriptive enough to show a date and time. So we pulled the last 24 hours worth. We parsed each string, again, comma-separated files, and then formatted that data in a pandas data frame. So we had a pandas data frame containing all 16 probes, containing 24 hours worth of data at each probe. And that made it really easy to plot our meteograms. So, So then we plotted our 5-panel meteograms. What are meteograms? Well, here they are. We have time on the x-axis, and then we have our values for each variable on the y-axis. So showing this is really useful when you're concerned with weather change through time. And so, for example, an example I have for you here is that this station in particular is the meteogram I'm showing you, because again, it's just over one station through time. First, it experienced a cold downdraft from this storm, a cold pool, and so that changed the wind direction and the wind speed, which you see here, and that changed the relative humidity, and that changed the station pressure. Then, not too long after that, that boundary I talked about moved over it, and so it was sort of like a dry boundary. It had dry air behind it, and so the relative humidity dropped off, the wind direction changed again, and our station pressure started to increase. So it's just a lot of time data that is what we were looking for, is we wanted to see how that data changed in time. And so that was really helpful because we were able to do each one of these every 5 minutes for each of the 16 probes. And we also needed to monitor battery power because some of our sensors required a battery voltage above 8 volts, and in an extremely cloudy area, you get concerned when your power is being supplied through a solar panel. We also used car batteries to power these things. So the solar panel charged the car battery, which then could run the station for up to 2 days, but there were some times where cloudy days lasted longer than that. So that's why we were most concerned with that. So how do we do that? I'll just show you a quick example with wind speed, which is colored in blue, wind speed max recorded over each minute, which is red dots, and then the wind direction, which is black dots. And if you've ever had to code or plot wind direction, it's not the easiest thing in the world, because if you think about a compass, 360 is the same as 0, right? That's north. So 350 is very close to 10, even though in math world, it's not. And so we just kind of made that easier for our viewers on the right-hand side, where we had, this is the northwest direction, this is the southeast direction. And we were able to do that. I talk about that on the next slide, sorry. But so we just used matplotlib to create all these. We used the pandas data frame. The index was time. So we just simply plotted the index on time and formatted it to make it readable. And then we filled for wind speed and put red dots for wind max to make it visible over one another, which is what I talked about down here. And then for wind direction, we just separated it into the y-ticks that we have here. We were able to make it so, and that's why you plot it with black dots as well, so that way, you know, it's not necessarily a continuous line. We needed a different y-axis, but this Meteogram plot code is currently working on being implemented into MetPy. We have an example up right now, and it's still being worked on. But hopefully this 5-panel plot Meteogram code will be able to plot whatever data you want from whatever source you want. And so if you're interested in that, it will be implemented into MetPy rather soon. So this was all StesoNet observations. This was all to do with our weather stations in a 16 grid. However, we also did other things during Vortex Southeast. There were balloon launches. And I'm not sure if anybody's familiar with SciPy here, but we used our balloon launches, which you see down here in the bottom right, releasing a balloon in Alabama. We are using these balloon launches and the radio signs. We're able to grab a vertical profile of what the atmosphere looks like from our particular point. Here's an example of what SciPy produces using balloon data. And so all we had to do was we had a tab-separated file. It was then converted into SciPy code, which was relatively easy, which you have down here. It just puts it in the header in the format that SciPy needs. And then it just SciPy executes the code and calculates all the variables for you and is able to produce things like this. This wasn't quite as real time, but as soon after the balloon was launched, we could do it right away. So that was nice. We were able to see the kind of data that we wanted to see. Learn about how unstable the atmosphere is and everything. So that was really helpful, just some of the other Python. So in summary, thank you for letting me give this talk. It was, again, Vortex Southeast needed our new approach. We decided to do real-time data because other mesonets around the country do real-time, and so we wanted to see if we could do it with our portable systems, and we did. And I hope you found it interesting and enjoyed it. Thank you. Pretty impressed. I hit exactly 22 minutes. I was pretty proud of myself. Any questions? Yes. It was actually designed starting by students at Texas Tech University. It uses LabVIEW to organize all the instruments on it, and then it has a data acquisition system. And we are able, they were designed for short fuse deployments and hurricane deployments where you set them up in 2 minutes and then take them down 15 minutes later, try to get them in a storm. But we were able to use them for this project in a semi-permanent state to kind of get, because Alabama does not have a mesonet, and so we wanted to make sure we could catch them as a scale weather. Mm-hmm.
So this is a great process talk. Is there any science results you could allude to from this great work?
Right. So we're working on that. In fact, we just got the grant for analysis because this just ended in May. And so we're working on that. A lot of things people are working on is sensitivity analysis. So like they're using the data we gathered from the StesoNets to kind of input into one of our current high-resolution models to try to see if having closer observations closer together can improve what the models are doing. We're getting some decent results there, and then we're also doing other sensitivity analysis for what we called observation targeting, where we want to try to figure out, okay, if it's cold here now, what's it going to do later, and maybe that will help us out. So yeah, I don't have a whole lot to show you right now. So. Oh, okay, you go ahead, in front. I'm not extremely familiar with that, but we just used a cell modem from the stations and just plotted it over the network. There weren't, from what I heard from people who work directly with the stations, there weren't a lot of issues with the bandwidth. I think they were able to send it over relatively easily, but I'm not, I think so. I'm getting nods over there, so I think so.
So for the great talk, it was really pleasing to see part of the instruments mounted in an NSF project
So this was done relatively quickly because the project was soon after we had the AWS, the interacting with radar data on the cloud. And Cartopy, we really wanted county lines, and we needed to import a shape file. We didn't have quite the time to figure it out, so we used basemap.
Keep on answering questions. Oh, man, you don't mind splitting.
Oh, yeah.
Yeah, go ahead, feel free to answer a couple questions.
Just a couple of general questions about tools and process adoption within your Admiral group and in the bigger context of the university. Like directly running, how many people are using Python with distros? Is there a large adoption of control?
Yes. So Eric Bruning, who will give a talk after this one, he is a big proponent. We've actually had a software carpentry at our location for 2 years in a row. Python is used in all areas. We use it to process model data. We use it to process real-time data. We use it for a lot of visualization. A lot of matplotlib is being used, and even in our classes and everything like that. Git, yeah, I've got a GitHub page. The version control is definitely in use a lot. So, great. Yeah, good question. All right. I think that's all.
Thanks, Don.
Thank you.